A modern CPU executes billions of operations per second. Inside the core, a single instruction takes just zero point 0.3 nanoseconds to process. But to execute those instructions, the processor needs data, and the primary repository for that data, main RAM, takes anywhere from 60 to 100 nanoseconds to respond to a single request. If a processor running at sub-nanosecond speeds had to fetch every piece of data directly from main memory, it would spend up to 99% of its life totally idle, waiting for electrons to physically cross the motherboard. Computer scientists refer to this widening gap between processor computation speed and memory access time as the memory wall. Ideally, we would build a single storage drive that is infinitely large, instantly fast, and costs practically nothing. Physical constraints and manufacturing economics make that impossible, so hardware engineers don't rely on a single perfect component. Instead, they build a layered ecosystem of storage technologies designed to trick the CPU into seeing zero latency. This diagram illustrates the memory hierarchy. It is a structured arrangement of storage technologies where access speed prioritizes the top and total capacity anchors the bottom. At the absolute peak are the CPU registers. They deliver data in under 1 nanosecond, but they are incredibly constrained, holding only a few kilobytes of data at most. Below the registers sits the SRAM cache memory, acting as a high-speed buffer. Below that is the main system RAM, where the bulk of the active data lives. The golden rule dictating this structure is cost. Faster memory technologies cost significantly more per bit, forcing hardware architects to use them sparingly. Looking at the schematic of the actual silicon, you can see how this hierarchy maps physically onto the chip. The cache itself is divided into tiers. Level 1 cache is extremely small and built directly inside each individual CPU core. Despite the limited physical size of the cache, modern hardware architectures successfully guess what the CPU needs, achieving hit rates between 90 and 99%. We quantify this efficiency using a metric called effective access time, or EAT. The formula multiplies the probability of finding the data by the time it takes to retrieve it from that specific level. Let's apply real-world constraints to this. Assume a conservative 95% hit rate, a fast 4 nanosecond cache, and an 80 nanosecond stick of RAM. The cache lookup costs 3.8 average nanoseconds, and the 5% chance of a miss adds 4 nanoseconds. That brings the total effective access time to just 7.8 nanoseconds. By maintaining a high probability of accurate guessing, a system relying heavily on 80 nanosecond memory operates as if it has 7.8 nanosecond memory, a mathematical illusion that prevents the CPU from starving. How exactly does a tiny 64 kilobyte cache successfully predict what to pull from a 16 gigabyte pool of RAM 95% of the time? The answer is the principle of locality. Computer programs do not select memory addresses at random. Software access patterns are highly predictable. This chart illustrates the two forms of that predictability. The first is temporal locality. If a program uses a specific variable, like a counter in a loop, it is highly likely to request that exact same piece of data again in a very short window. The second form is spatial locality. Because structures like arrays and lists are stored in sequential memory blocks, if a program reads one piece of data, it will almost certainly read the data physically adjacent to it next. Think of large-scale Indian infrastructure, like the IRCTC railway network, or a UPI database processing an array of millions of sequential transaction IDs. When the CPU requests transaction number 1, the cache controller leverages spatial locality to automatically prefetch transactions 2 through 10 into the local L1 cache before the CPU even asks for them. Cache hardware is engineered entirely around these two behavioral quirks. If developers wrote code about requested memory addresses in completely random intervals, the cache would fail. To make this prediction engine function, architects must solve an algorithmic routing problem, efficiently mapping gigabytes of main memory into just a few megabytes of available cache slots. This diagram outlines the mapping strategies. The simplest approach is direct mapping, where each memory block is assigned to one fixed slot. It is incredibly fast to search, but it has a fatal flaw. High conflict rates occur if two critical variables are forced to fight for the exact same slot. At the opposite end is fully associative mapping, where data can live in any available slot.
This provides ultimate flexibility, but searching every single slot simultaneously requires slow, expensive, power-hungry hardware. The modern industry standard is set associative cache. Memory targets a specific set, but within that set, the data can land in one of multiple available ways. This hits the perfect balance between lookup speed and placement flexibility. Reading data is only half the execution cycle. When a CPU modifies data, it must decide when to update the slow main RAM. A write-through policy updates the RAM instantly alongside the cache, ensuring perfect data consistency, but generating heavy bus traffic. A write-back policy is far more efficient. It updates only the cache initially and delays writing to RAM until the modified data is finally evicted. Set associative mapping and write-back policies work together to keep data off the main system bus, preserving crucial bandwidth for the rest of the computer. In the real world, the physical constraints of hardware engineering directly dictate the daily work of software developers. Elite engineers at companies managing massive data loads do not rely on compilers alone to process their logic. They actively write cache-friendly code. Simply choosing to structure data sequentially, by using continuous arrays rather than scattered linked lists, guarantees spatial locality. This decision alone can result in execution speeds up to 100 times faster without changing a single step in the actual algorithm. For engineers preparing for systems design interviews, the most potent optimization you can make isn't always reducing algorithmic complexity. Often, it is minimizing cache misses. The computers we rely on do not actually possess memory that is simultaneously terabytes in size and nanoseconds in speed. Through intelligent hierarchy, statistical prediction, and precise spatial engineering, the modern computer architecture projects an absolute illusion of perfection. Because, as the foundational principle of computer science proves, memory is the bottleneck, but cache is the solution.